Hi, today we will talk about Chapter 5. Chapter 5 is talking about a new technique in algorithm design. It's called divide and conquer. So this technique, we will take example to show these techniques. So let's talk about this technique in general. In general, divide and conquer, when we want to solve the problem, we break up the problem into several parts. So we have the problem, we break it into two smaller problems and we try to solve every problem alone, and then we merge the solution to get a solution to the initial problem. So we break up the problem into several parts. We solve each part recursively. So again, each part of these two parts, we break them into two smaller parts, and so on. And then we combine usually the solution to the subproblem into the overall solution. So this is the general techniques. I think we talked about this in the chapter 1, merge sort, and we will again talk about this in this chapter. So the most common use in the break, divide and conquer, we break up usually the problem of size n into two equal parts of size n over 2. So this is the usual thing that we do. And we solve the two parts recursively, and then we combine the two solutions. Usually we combine it in linear time. So when we merge the solution of the two parts, we need to find an efficient merge so that it's linear time, it's big O of n. So why we use divide and conquer? We use divide and conquer because we will get efficient algorithm if we use it. For example, if we use like traditional sort, like bubble sort or selection sort, usually we get efficiency n square. But if we use divide and conquer, like merge sort, we will get n log n. And n log n is much better than n square. For example, if the number of the array is 1000, we will get like 1 million operation. If we use bubble sort, we will get 1 million operation. But if we use the 1000 array and we use merge sort, so we will only use like we will use n log n, so 1000 multiplied by log 1000, which is like 10. So 10 multiplied by 1000, it's 10,000. So here we need 10,000 comparisons, and here we need 1 million comparisons if n is 1000. So you see there is a big difference. In this chapter, we will take 3 examples about divide and conquer techniques. The first example I think we are a little bit familiar with is the merge sort. So merge sort is using the divide and conquer technique. Let me show you a demo that you remember what is a merge sort. So in the merge sort, we have array of unsorted values. Here we have like array of size 8, and we have 8 values. Let's try to see how the merge sort will work. So we go step by step. So the first step, we will divide this array into 2 arrays. Every array has 4 elements. And again, this array we divide it recursively into 2 parts. We have 2 arrays, every array is 2 elements, and we take one, and again recursively we divide this array into 2 sub-arrays. Every array is 1 element, and then the array with 3 is sorted. So if the array size is 1, we don't need to sort it, right? It's already sorted array. So same like 9 is sorted. It's the only element in this array, so it's sorted. Now we come to the merge operation. We need to merge these two solutions. So we have a sorted array that has elements 3, and a sorted array that has element 9, and we want to sort them. How to sort them? We make two pointers, one pointer on the 3 and one pointer on the 9. We select the smallest, which is 3, and we put it here, and then we select the 9 and we put it here. So now we merge the two sorted array into a bigger sorted array of size 2, and this array, the 3 and 9, is sorted. So this is sorted array. Now we go to the other array. We do the same. We divide them. They are sorted. 2 is sorted, 5 is sorted, and then we sort the 2 and the 5 using the pointers. So we get 2 and 5 are sorted. And now we need to merge the two solutions. So we have two arrays. Both of them are sorted. We need to merge them to get a sorted array of size 4. How to do this? We make a pointer on the 3 and a pointer on the 2. So which one is smaller? The 2 is smaller, so we put it here. Then we move the pointer to the 5. We compare 3 and 5. Which one is smaller? Is the 3. So we put it here. And then we compare the 5 and the 9. We move the pointer. So 5 is smaller. We put it here. 9 is smaller. We put it here. So this is the merge operation. So now we have a sorted array of size 4. But the other array of size 4 is not sorted yet, so we have to repeat the same operations like before. We break it up into parts till we have array of size 1, and then we merge. Again, we do. So here we have to merge this. We compare 1 with 4. 1 is the smallest. We take 1, and then we compare 4 with 6. 4 is the smallest. We take 4. 6 is the smallest. We take 6 and 8. So now we have two sorted array of size 4. So we have again to merge them to get this full sorted array of size 8. So again we will have pointers, one pointers to the 2 and one pointers to the 1. Which one is the smallest? For sure the 1 is smallest. Then we move the pointer to 4. Which one is smallest? The 2 is smaller than 4. And we move the pointer to 3 and 4. Which one is smaller? 3 is smaller, and so on. So we keep moving till we get a sorted array. So this is the idea of the merge sort. I hope it's clear by this demo. So let's go back to the slides. So in the merge sort, we are giving n elements, and we want to rearrange them in ascending order, or we can be also in descending order. So what's the application of this problem? It's clearly we want to sort, let's say we want to sort names, we want to sort files by the size, we want to sort Google PageRank results. This is like direct applications of the sorting. We can also sorting can be used to find a medium, to find the closest pair problem, or in the binary search. So remember binary search, before we do binary search we need to sort the array. So sorting is used also in binary search before we start binary search. So merge sort, as we discussed, you have to divide the array into two halves, and recursively you have to sort each half. And then after you sort them, you have to merge the two halves. So sorting can be also done by like you want to sort the letters. So here we have array that contain letters and not numbers, and we want to sort these letters in alphabetical order. So at the end we will get something like this. A is before G, is before H, before I, before L, before M, before O, and so on. Okay? So this is the goal of this example. So how to do this? First we want to divide the array into two parts. This operation take only big O of 1, right? Because it's easy to divide the array into two parts. Just mark the first part from index 0 to index n over 2, something like this. So it's easy to divide. Now you need to sort every array. So sorting, how much does sorting takes? We have two arrays, every one of size n over 2. So we have 2 times the number of comparison we need to sort n over 2 array. So that's why we have 2t n over 2. We will discuss this later. And then to merge array, to merge the array, remember how to merge. We make a pointer here and a pointer here. So we compare A with H. Which one is smaller? A. So we delete A and put it here. And then we move the pointer to G. We compare H and G. Which one is smaller? G is smaller. So we put it here. And then we move the pointer. We compare H with L. Which one is smaller? H is smaller. So we move it here and we move the pointer. We compare L with I. I is smaller. So we move it here and we move the pointer. We compare L with M. L is smaller. So we put it here and we move the pointer to O. O and M. M is smaller. So again, we move the pointer here. S and O. O is smaller than S. So we put O here. We move the pointer. R and S. R is smaller. We are done with this array. And then we are left with S and T. So we move them here. So this merge operation, it takes big O of N. Because it's like for every character here, you just do one comparison, right? So that's why we have n characters. So you have big O of n comparisons to merge using this merging algorithm, using the pointers. And now, so combining how to merge efficiently, we have a linear number of comparison, big O of n, as we saw. Okay. And we use the techniques that we explained before. So this is just to explain it again. We compare A with H. A is smaller. We put H here and we move the pointer and so on. Okay. So actually we can do this we can do this in place, like in the same array. We don't need to have an extra array. So now to discuss the efficiency of the merge sort, let's look to this tree. So usually we have array of size n, right? To sort this array, we need t of n. What the meaning of t of n? T of n means that t of n is the number of comparison I need to sort array of size n. This is equals to 0 if the size of the array is 1. If the size of the array of 1, it's sorted. I don't need to make any comparison, right? So this is the base case in the recursion. And this is equal to 2n over 2 plus n operations otherwise. Like, imagine you have array of size 2. Let's say 7, 3. I need t of n to sort this array. So is n like 1? No, n is not 1. It's 2 here in this example. So I have to go here. So this is equal t of 2 equal 2 times I have to sort array of size 1. Sorry, 2 times t of 1 plus n. What is n? 2. Why is this? Because if I have array of 2, I have 2 times, I will divide it to 2 arrays, array of 7 and array of 3, right? I have to sort this array and this array, and then I have to merge them. To merge them, I need to do n comparison, 2 comparison, because I have 2 elements. So in total, I need two operations to sort them, right? To merge them, sorry. So I need two t of 1. T of 1 in this case is 0. So I don't need any operations here. I just need the operation to merge the two elements. So t of 2 in this example is just 2. Okay? So this is called the recursive formula that we can analyze when we want to analyze the merge sort. But there is easier way to analyze the merge sort is to consider the tree, merge sort tree. What is the merge sort tree? So usually here we have array of size n. We divide it into two parts, n over 2, n over 2. And in every part we divide n over 4, n over 4, and so on. At the end, we will get arrays of size 2, arrays of size 2, and so on. And this array of size 2, actually we can divide it to array of size 1, but we ignore this because in this step we don't do any comparison. That's why we ignore these steps. Now, let's come to this array. Like imagine we do the division and then we come back. Let's assume we come back to here. So here we have sorted array here, and we want to merge it to this array. If you want to merge it to this array, what will be, if you want to merge it to this array, you need n operation for the merge operation, right? So to get this array from these two arrays, we need n operations. Okay. طيب. To get this array, how much we need? We need 2 times. Okay, we need to get this array, we need n over 2 for the merge operation because we want to merge this and this, right? And to get this array, we need n over 2 operations because we want to merge this and this. So in total, we will get for this level, we will get 2 times n over 2 merge operation or comparisons. So actually we need, this is also n, right? 2 multiplied by n over 2 is also n. But for this level, how much we need? To merge this array, we need n over 4. To merge this array, we need n over 4, n over 4, n over 4. So we need 4 times n over 4, which is also n. So what you notice, every level, to merge every level, you need n. Okay? Now the question, how many levels we have? Actually, we have log n to the base 2 levels. Why is that? Imagine we have like 16, array of size 16, n is 16, so you will get 8, 8, and then you will get 4, 4, 4, 4, and then you will get 2, 2, 2, 2, 2, 2, 2, 2. How many levels we have? 1, 2, 3, 4. So we have 4 levels. But this is exactly like log 16 to the base 2. It's 4, right? Because 2 to the power of 4 is 16. So the number of level, if you divide the array, if you keep dividing the array by 2, you will get log n levels. And every levels I need n comparison in the merge operation so that the efficiency of the merge sort is n log n. So this is what we will get, n log n. This is the efficiency of the merge sort. So as assignment for this exercise, we need to implement merge sort. So try to search one code. I'm fine if you look one code on the internet and to see how to implement merge sort. but you need to modify this code to try to count the number of comparison. So every time you find comparison, try to count it. And so after you run the algorithm, let's say you have array of size 8 and you run the algorithm will print you a sorted array and also will print you the number of comparison. In this case, it's expected to be n log n 8 multiplied by 3. So you should get, like, to sort array of size 8, you need something close like to 24 comparison. So to summarize, in this video we learn about new techniques called divide and conquer, and we take one example, the merge sort. We find that merge sort is n log n. This is much more efficient than the standard sorting algorithm like bubble sort or selection sort. And we find out how to analyze it. We show a demo for merge sort, and we give assignment to implement the merge sort. So I hope this video was clear, and see you in the next video.